Over the next hour in this session, 3 different presenters will showcase their exciting work related to blue carbon in the region, highlighting the value and benefits of carbon sequestration, tidal wetland carbon storage potential, and the economic value of carbon sequestering ecosystems. Climate change pressures can be felt across the mid-Atlantic. These changes can lead to a shift in marine species due to warming waters, an increased fluctuation in weather patterns that could affect seasonal tourism and human health, and can alter ecosystems due to changing ocean chemistry and rising sea levels. Communities are learning to adapt with new and innovative strategies to mitigate the current and future impacts of climate change. One strategy that will be discussed in detail during this session is conserving and restoring coastal ecosystems, which provide carbon sequestration. This is also known as blue carbon. Mangroves, coastal forests, seagrass beds, and salt marshes are all blue carbon ecosystems. They are all tremendous carbon sinks and trap carbon dioxide in their deep organic rich soils for hundreds to thousands of years. This topic not only has a global reach in its ability to help curb rising atmospheric carbon dioxide levels, but provides a multitude of other ecosystem services, such as coastal habitat, water quality improvement, and land protection from coastal storms. Additionally, blue carbon may provide economic value by avoiding the cost of climate change. We will learn more about the immense value of these ecosystems and the progress we are making for using blue carbon as a mitigation strategy in this session. I am pleased to welcome our speakers, and I thank them for joining us today to present their work on blue carbon in the Mid-Atlantic. Finally, I'd like to thank everyone in attendance for joining us today. I hope you're as excited as I am to learn more about the opportunities we have in the Mid-Atlantic for exploring blue carbon as a strategy to abate climate change, and hope you will stay tuned for the poster session at the conclusion of this session. So now on to the show. Our first speaker is Metthea Yepsen. Metthea is a wetland research scientist in the Division of Science and Research at the New Jersey Department of Environmental Protection. Her work focuses on blue carbon, tidal wetland monitoring, and developing tools to improve wetland restoration decision-making. Metthea's talk is titled Blue Carbon as a Climate Mitigation Strategy in New Jersey. So apologies, everyone. I think we're having a slight technical, not technical glitch, we're looking for Metthea. But if you can just hold tight for 1 minute.
Hi, Kari, not to interrupt, just wondering whether we should move on maybe to the next speaker in this session and we can come back to Metthea when she's available.
Yeah, I'm gonna look to Daniel, would you be okay jumping up ahead 15 minutes and presenting now?
Yeah, that's fine.
Perfect, thank you. It wouldn't be a fun virtual conference if we didn't have one thing go slightly astray. So we are in the adaptive management business, so this is what we do. So we are going to move on to our second speaker, who has graciously decided to be our first speaker, Dr. Daniel Warner. Dr. Warner received his PhD in water science from the University of Delaware and is now with the Delaware Geological Survey. His research background focuses on geospatial techniques for mapping and modeling ecological processes at different spatio-temporal scales. Dan's talk is titled Mapping and Modeling Blue Carbon Storage in Delaware Coastal Wetlands. So without further ado, I'm going to hand it over to you, Dan.
Share my screen here. Okay, hopefully everyone can see my screen. Yeah, so my name is Dan Warner. I work at the Delaware Geological Survey. This work was done with co-PIs John Callahan and Tom McKenna, who also worked here, and with a lot of help from Kari as well. This is originally an on-demand presentation, so hopefully nobody watched it during the break and is immediately being subjected to it again. But without further ado, here we go. I'm going to talk about mapping and modeling blue carbon storage in Delaware's coastal wetlands. So this is a blue carbon session. I guess if I'm the first speaker, I'll dwell on this a bit more. Why do we care about blue carbon? Well, coastal wetlands accumulate and store carbon at much higher levels than other ecosystems, even though they have a pretty small aerial extent on the Earth's surface. This is because of high plant productivity and slow rates of decomposition in the wet soils. But the amount of carbon that's stored in these systems is difficult to estimate. It can be both vertically challenging because the carbon concentrations vary with depth and with variable sediment thicknesses. We don't know, on a per square meter basis how much carbon is in this column of sediment. And storage also varies in space due to various environmental factors. So if we want to start mapping and modeling carbon storage, we have to consider what potential factors might influence where carbon tends to accumulate and at what levels. So in this study, we considered hydrology, thinking about what parts of the marsh flood with different frequencies and what parts of the marsh are accessible through different flow paths. I also considered vegetation, different species, different growth forms, density of vegetation stands could all influence the carbon content of the soil beneath. And also consider chemical and sediment inputs, what sort of sediments are coming from the uplands, what sort of inputs are coming from the marine environment. And there's also quite a bit of transfer within a marsh system as some sections might erode and then deposit in other areas. So some of the key questions of this work were, can we map organic matter storage on the marsh platform by combining field observations of carbon content with remotely sensed data? And the second question is, how much organic carbon is stored in our study area? These areas are on the right. You can see the Blackbird Creek Marsh and the St. Johns River Marsh. These correspond to the locations of the Delaware National Estuarine Research Reserves. And then we finally want to ask a bigger picture question of, what sort of things can we infer on the vulnerability of the stored carbon based on where we see it shake out in its spatial patterns. So the first step to doing this mapping exercise was we needed ground truth carbon data. And this is all based on sediment cores that were collected with hand augers. We kind of built off a data set that was already collected by Kari's group with Denner. This is a pretty big data set. A lot of the cores were collected along major channels and accessed by boat, I'm assuming. So we wanted to supplement this with other parts of the marsh that weren't well represented in this set. So we did a lot of access to the marsh on foot and collected samples from the marsh interior, and in a couple areas we went way upstream to sort of the headwaters of the marsh. Once we collected the cores, we segmented them from 0 to 30 centimeters, and then in skip 10 centimeters, 20 centimeter increment, and so on, to get a picture of sort of the vertical distribution within the top meter. And then we measured organic matter content using loss on ignition, as well as carbon content using a carbon, nitrogen, and sulfur elemental analyzer. And then to calculate carbon density or carbon storage, you actually have to normalize it based on the bulk density of the soil itself. So we also measured that. And we also collected several spatial covariates to use in our modeling. This included information on the terrain. So we took a DEM and calculated various derivatives from it, like slope, a ruggedness index, a detrended DEM, which sort of removes the overall landscape trends, so you see more localized topographic features. We also measured the Euclidean distance to the channel network within the marsh. And then we took data from the National Agricultural Imagery Program. And this is multispectral big data, so we can develop spectral vegetation indices like the NDVI, Normalized Difference Vegetation Index, GCI, which is things like Greenness Chlorophyll Index or something. I forget what CP stands for. Anyway, we did some preliminary modeling to narrow down the set of predictors that we were actually going to use. And we ended up with a final predictor set of elevation, Euclidean distance to the channels, and the NDVI. So to do this modeling, Whenever we collect soil cores, we had GPS coordinates associated with them. So we could take, at each observation point, we could also extract the corresponding values from our spatial data covariates. And then we fit models to our observations of organic matter density in the upper 30 centimeter of the marsh. And we considered several models: a general linear model, random forest model, a K nearest neighbors model, and a neural network. And then, as I mentioned on the previous slide, we selected our final set of predictors based on iteratively eliminating predictors from preliminary models and seeing how they affected model performance. And then we looked for potential autocorrelation to reduce variable redundancy in our final models. In the end, we selected a multiple linear regression. It performed pretty much as well as the other modeling approaches, or at least as well as the best modeling approaches. And multiple linear regressions are pretty easy to communicate and understand their internal structure compared to some of the more sophisticated machine learning models. We finally found a mean absolute error of our model of 6.1 kilograms per meter squared of organic matter in the top 30 centimeters, and an R squared of 0.28, which if you're like a laboratory chemist, that's a very bad R squared, but for a large spatial modeling exercise like this, it's pretty good. We found that the random forest model performed a little bit better than our linear regression, not that much to be, very substantial to our interpretation. But the random forest, the way that model structure works, is splits the data on it sort of partitions the data into groups, and that ended up putting a ton of weight on the Euclidean distance predictor variable. And when we went to extrapolate that model, it created really weird looking maps that were very almost cartoonish. So we stuck with the multiple linear regression. And then in the end, since these models are actually estimating organic matter density, since that's what we had the most data on, we converted that to an estimate of carbon density based on the carbon content of organic matter that was analyzed on the elemental analyzer. We did this by doing some of our samples, the raw samples analyzed for total carbon, and then other samples we took the ashed residues that were left behind from the loss on ignition analysis and measured total carbon in those. By subtracting the two, we know what fraction is organic. And so in the end, we extrapolated the model so we can see sort of where model predictions were highest for organic matter storage. So from these maps, you can see that sort of near stream and these areas that are closer to the marsh outlets are generally tend to have a higher carbon density predicted by the models. So these areas are also generally higher elevation, like they're what you consider the high marsh. And then as we move upstream into these areas, it became much lower and consistently flooded. And so what's that mean for potential exposure to inundation? Here we just did a simple bathtub model simulation of the mean higher high water mark within these marsh systems. This isn't the most sophisticated approach. It doesn't consider like attenuation of tidewater because of surface roughness from vegetation. It doesn't simulate the water going up individual channels or anything. So you can definitely get way more complex with this, but this is kind of a quick proof of concept. We saw that generally the Blackbird Marsh on the left is much lower lying. A lot more of that marsh surface got inundated frequently. Whereas St. John's Marsh, we see a lot of the near outlet areas are sitting above mean higher high water. And these correspond to the areas where we predicted the highest carbon storage. In the end, we estimated that respectively, Blackbird and St. John store 70 and 79 gigagrams of organic carbon in their top 30 centimeters. This is clearly an underestimate because we don't know how deep the sediments are across the marsh platform. So that's an area of future research, is trying to understand sort of the 3D structure of these marsh sediments. And since we found that carbon storage was highest in the high marsh and near channel areas, these areas are less frequently inundated, but they kind of correspond to areas where you'll frequently see boats driving really fast down the main channels. These boats create big wakes, and those wakes are potentially sources of erosion for these high carbon storage areas. So looking forward, we're looking to incorporate some predictors from a more recent project looking at LiDAR DEM corrections in salt marshes to kind of go back and look more into modeling carbon storage. We can investigate more sophisticated inundation models instead of just the bathtub, which doesn't really simulate the natural system at this fine scale very well. And then we can hopefully do investigations of three-dimensional marsh structure in the future to see like depth to sand, and that'll help us estimate how much carbon is stored in the entire system. So with that, thanks to Delaware Estuarian Research Reserve, the DNREC, and City of Dover, who helped us get all sorts of land permission access requests processed. Thanks.
Thank you so much, Dr. Warner. And just as a reminder, feel free to drop any questions you have in the chat, and there will be a Q&A at the end. And so now we are going to introduce our second speaker. Metthea is here, and she is going to be giving a presentation titled Blue Carbon as a Climate Change Mitigation Strategy in New Jersey. Metthea is a wetland research scientist in the Division of Science and Research at the New Jersey Department of Environmental Protection. So I'm going to take it over to you, Metthea. And
thank you very much. My sincere apologies for being late. And Daniel, thank you for jumping in and going first. Okay, I'm going to share my screen. Okay, are you seeing my note slide?
we are seeing the slide with your notes, not the presenter view.
All right, shift that up here. Having trouble accessing, switching. Hold on, I'm going to stop sharing and then go again.
Go down to your lower right on your PowerPoint window, and there is a screen there. Press that and it'll bring it up.
Down to the, okay. Sorry.
That's it.
Okay, are you seeing the right one now or still not?
Looks perfect.
Okay, okay, so you can see not my note slide. Okay, thank you. Sorry, bear with me. Thank you for bearing with me.
Certainly,
okay.
and you can. Everyone can set that up when they're going to their window. They can set it up ahead of time, so no one ever has to look at the PowerPoint window.
Got it. Okay, so I think we're in a good spot now. So thank you again for bearing with me. So good morning, my name is Metthea Yepsen, and I'm a wetland ecologist and research scientist working in the Division of Science and Research at the New Jersey Department of Environmental Protection. And today I'll be talking about how blue carbon is being used as a climate mitigation strategy in New Jersey. So first I'll talk about the need for carbon sequestration, and then talk about what blue carbon is. I'm sure Daniel probably also discussed that as well. And then I'll highlight 3 projects that we are working on that are advancing our climate mitigation work in New Jersey. So as we all know, the climate is warming, and in order to prevent even more extreme warming in the future, we have to change our emissions that are happening. So in New Jersey, we have some ambitious targets that we've set for ourselves for 2030 and 2050. By 2050, we're hoping to reduce New Jersey's emissions by 80% of the 2006 baseline. And it's been determined that in order to do that, we have to incorporate carbon sequestration. So it's not just enough to decrease the amount of carbon and carbon dioxide and methane that we're releasing into the atmosphere. We also have to pull that carbon dioxide out of the atmosphere in order to meet our goals. So what I'll be focusing on today is carbon that is pulled out of the atmosphere and stored in salt marshes and SAV. We call this blue carbon. So the way that this works, and again, forgive me if Daniel already went into this, but plants pull carbon dioxide out of the air, and as part of photosynthesis, they store that in their leaves and stems and in their roots. And then as those plants and plant materials die, they become leaf litter and root mat litter that is incorporated into the soil, and that carbon that was pulled out of the atmosphere is sequestered in the soil. What makes salt marshes and seagrass so fantastic is that they are flooded, regularly flooded, and that flooding decreases the amount of respiration that happens in the soil. So the carbon that's stored in the soil is eaten by microorganisms, and those microorganisms, as a byproduct of respiration, release gases, climate warming gases back out into the atmosphere. But that process slows down when those sites are flooded because there's less oxygen available. And so while forests also sequester a lot of the carbon that they sequester is re-emitted. But in wet systems, there's less oxygen available, and so there's less decomposition and less of the biomass is re-released as greenhouse warming gases back into the atmosphere. And so it's estimated that tidal wetlands and seagrasses can sequester carbon at rates of 10 times greater than forest per unit area. So in New Jersey, we have nearly 300,000 acres of tidal wetlands, and they're a defining feature of our coasts, along with beach towns and boardwalks. And a majority of the wetlands are owned and managed by the state. The tidal wetlands are valued for coastal resiliency benefits, as habitat for recreationally and commercially important fish and bird species, for their ability to clean water, and now we're beginning to appreciate them for the role they play in sequestering carbon. So today I'll be talking about 3 different projects we have where we're looking at using blue carbon for sequestration in New Jersey. So the first is a natural and working land strategy that we're currently developing. The second is through our participation in the Regional Greenhouse Gas Initiative. And the third is in the Coastal Ecological Restoration and Adaptation Plan. So the natural and working lands strategy is a plan that the DEP is working with along with the Department of Agriculture. And the goal here is to draft an evolving natural and working land strategy that identifies and implements detailed strategies that will mitigate the impacts of climate change through carbon storage and sequestration. And so we're doing that by looking at which activities we can do in forests, in agriculture, grasslands, wetlands, developed lands, and in with our aquatic resources to be able to increase the carbon sequestration in those areas. The second thing that we're looking at is through our rejoining of the Regional Greenhouse Gas Initiative that we call that RGGI. So New Jersey officially rejoined RGGI in January of 2020. And RGGI is a multi-state market-based program that establishes a regional cap on carbon dioxide emissions and requires certain fossil fuel power plants to obtain an allowance for each ton of carbon dioxide emitted annually. New Jersey gets a percentage of the funds generated from the auction of those allowances. And so we released a strategic funding plan that identifies which programs and projects will receive funding in each 3-year increment. So 10% of those auction proceeds are dedicated to the funding of blue carbon and terrestrial sequestration projects in the state. So as of now, those auctions have generated more than $15 million that can be used for carbon sequestration work in New Jersey. And what we're doing with that money is we just released an announcement for a Natural Climate Solutions grant. And this will fund on-the-ground programs that create and restore and enhance New Jersey's natural carbon sinks. So the funding will go towards salt marshes and forests and SAV. And so some of the types of projects that we'll be looking to fund for blue carbon are living shorelines, tidal connectivity restoration, vegetation restoration, and SAV restoration. So we're pretty sure that this is one of the first grant programs to fund specifically blue carbon projects in the state, and we're quite excited about it. So in terms of what makes a good blue carbon project, after doing some research, we came up with a couple of different buckets. So the first is projects that increase salinity in tidal wetlands. So wetlands in general are notorious for sequestering large amounts of carbon, but in freshwater systems, they also release a fair amount of methane. So when we have tidally restricted tidal wetlands, like this area here, this is a salt marsh near Cape May, where because of beach fills and development that's happened, the tidal channel is smaller than typical and often closes up. And so what happens is that although we have high salinity out here, we often have lower salinities in here. And so this becomes a source of methane. And methane is a much stronger greenhouse gas than carbon dioxide. So the methane that's emitted ends up offsetting a lot of the carbon sequestration benefits of this site. So there's a project in place to make this tidal connectivity wider and wide enough to be self-sustaining. And that should turn this into a tidal marsh that has sort of a net carbon sequestration benefit. So we're looking at projects like that. We're also looking at projects that will protect carbon that's stored in the salt marsh. So as Daniel mentioned, erosion is a big issue when we're thinking about protecting this stored carbon sources. So here we have an area of marsh that has rapidly decreased since 1939 due to erosion. And as these carbon-rich soils are eroded, some of them are exposed to oxygen, which then increases the amount of carbon that would be re-emitted back to the atmosphere. And so to fix that problem, we can look into living shorelines that will help prevent erosion. Another option is to restore vegetation in drowning salt marshes. So this is another area in the Delaware Bay that used to all be marsh. Because it was diked and there were other human manipulations, this has lost elevation and has lost vegetation over time. So right now, this is probably a net emitter of carbon because these carbon-rich soils are not bound in place and not protected by plants. And so they're probably losing some of their carbon dioxide and carbon and re-emitting that back to the air. But this is an area that we could potentially revegetate. And then we would not only be protecting the carbon that is stored there, but also it would begin to sequester carbon through the addition of plant material. And then finally, we can facilitate marsh migration to protect salt marsh migration zones. So we have maps in the state that are predicting where marshes will migrate inland as sea level rise. So these pink areas here are areas that are currently upland. They're not influenced by the tides, but as sea level rises, we expect them to be flooded and to turn into salt marshes. This is a little bit of a tricky one because often they're moving into forests, which also have a large amount of carbon sequestration. And salinities in the future are a little bit unknown. So we're still kind of working on this, the science behind this, but it still seems like a good idea to protect those areas for the future. And finally, we are working on a coastal ecological restoration and adaptation plan. So this is a project that was funded by an EPA wetland program development grant. And it has two major components. The first is a participatory GIS project with community members and stakeholders. I know that Marco has done a bunch of work on that in the past. So we got people who are interested in tidal wetlands from across the state to come and mark areas of marsh that they're specifically interested in or concerned about, or that they find to be especially important on the map, and also areas where they would like to see restoration projects happen. And these could be projects that are in any phase of development. And then we also collected a bunch of information about those projects. So who are the major project proponents? What are the goals of the projects? What phase are they in? Are they in planning phase? Do you have permits? Do you have funding? Information like that. The second part of the project was to develop statewide maps that could look at some of the issues of concern in these areas. Thanks, Kari. And so what we're doing for that is looking at things like which areas are going to be most important for protecting coastal communities from flooding and buffer them from storms, which areas are going to be most important for protecting specific wildlife, which areas are going to be most important for water quality improvements. And then the issue of concern I've been working on is this blue carbon issue. And so this color-coded map here is sort of a draft of what we have. And so it attempts to incorporate many of the things I talked about before, areas where we have potential for marsh migration, potential for marsh drowning, potential for marsh erosion, and then combining that with salinity. So we can find hotspots of places where if we were to do a restoration project or a protection project, we would get some good carbon sequestration value. And then we can overlay the areas that the community has identified as being important to them or where they want to do projects and try to line up the goals. And so with that, thank you very much for listening to me. And yeah, I'm happy to answer any questions. And thank you all for having me talk to you today.
Thank you so much, Metthea. I love a good photo of a soil core. We're going to move on to our third and final speaker, Charles Colgan. Charlie is the Director of Research at the Center for the Blue Economy with the Middlebury Institute for International Studies at Monterey. Charlie's talk is titled Estimating the Economic Value of Blue Carbon in the Mid-Atlantic. So I'm going to kick it over to you. It looks perfect, but we can't hear you if you were speaking.
There we go. Should be better now. Can you hear me
Perfect.
now?
Yep, loud and clear.
Okay. So my talk today is taken from a study that we did for Marco last year. We were asked to update and expand estimates of economic contributions of oceans and coasts in the mid-Atlantic area, and to begin to explore the economic value of blue carbon in the region. As Dan and Metthea have pointed out, there's a lot of blue carbon in the area. All of the Marco states have abundant wetlands resources, and in this particular map, we are showing the estuarine emergent wetlands from the NOAA coastal change program. We've also used the National Wetlands Inventory data for some of this work. So the areas that you see here are the areas that we are trying to estimate the economic value of. Now, Dan pointed out in his presentation, the starting point for all of this is on the ground measurement of sediments and chemical analysis at highly specific locations. So we accumulated a whole variety of observations from throughout the region and basically used those as use kind of the midpoint of the range of those various estimates of the amount of carbon in the soil as our basic carbon storage stock, if you will. We also borrowed some data from Duke University which had done a sequestration estimate for the states from New York to North Carolina, and for roughly the same wetland area. So we started with some information on the stock of blue carbon that exists and the change in the stock of blue carbon that is currently available through the sequestration processes that were described earlier. And from that, tried to estimate what is the economic value of both the sequestration and the storage. Well, so starting off with storage, the economic value of the stored carbon is essentially calculated on the assumption that it becomes unstored. That is, that the carbon in the wetlands is released over some period of time. And the value of that carbon remaining in the ground is essentially the value of the damages avoided from having that carbon emitted into the atmosphere. So this particular graph comes from our estimates for Virginia. The graph for the other states looks exactly the same, except the y-axis changes a little bit. So the blue represents the amount of carbon in the soil. This is from 2020 to 2040. We make some assumptions about the annual carbon release, which is the gray line at the bottom, because of the loss of wetlands, because of any number of factors that causes the sheer area of wetlands to decrease over a period of time. And what you get is the carbon in the soil being gradually reduced, as shown in the blue line, and the orange line represents the cumulative amount of carbon over that period of time that is emitted into the atmosphere. The next problem becomes one of what's the value of the carbon damages that are avoided because that carbon remained in the wetlands of Virginia. So what's the value how do we calculate that value? Well, there are two economic factors here. One is the actual value per ton, metric ton of carbon. And we used three different possible measures of that. The first was the RGGI carbon traded amount that Metthea referred to earlier. So the stocks, the Regional Greenhouse Gas Initiative program requires the purchase of permits for emitting. And those purchases are at a price. That price is reported in each of the rounds of auctions. And so we use the amount of the dollar price per metric ton that people were willing to pay in the Mid-Atlantic auctions in order to keep in order to buy the permit for emitting. That's a proxy for the value of the carbon. It is, however, a low value because the market for RGGI credits is actually pretty immature, and there's not a lot of power plants being built in the region, so that the amount of money flowing into these credits is relatively small, at least in short periods of time. The other option we used was the social cost of carbon. And the social cost of carbon is estimated by the federal government. It is a proxy for the damages to the global economy from each metric ton of carbon greenhouse gas emissions emitted. We used a kind of the operative estimate of around $140 per ton. At the time we did this study, There's also a very high impact value, which basically says if there's a lot of emissions and a lot of damages from climate change, then the value of not adding to that climate change damages, those climate change damages goes up. And it's the so-called SCC high impact. I should point out that that the social cost of carbon has since been declared illegal by a federal judge, and so the dollar value of the judge determined that the social cost of carbon was $1. I won't go into that. That's for the legal arguments. So then we looked at the annual flows of carbon removed, and we estimated that the blue line represents the annual additions to carbon storage or sequestration, the sequestration effect. And then we have to, because this happens out over 60 or 70 years, we have to discount that back to present value. We use a very low discount rate here of 1%. So the result of all of this is that from the regional point of view, and our report contains data for each of the states, under the RGGI pricing, there's about $1 million in stored carbon. Under the social cost of carbon, there's about $8 million worth. And under the high impact carbon, there's about $26 million worth. Annually, the region is sequestering. I'm sorry, I got the decimal place. So it's $1 billion in storage, 8 billion in stored carbon at SCC, and 26 billion. Annually, it's sequestering about $140 million at the RGGI price, and up to about 3.5 million. Annually, the total discounted present value of the sequestered carbon over 40 years at the high impact cost is about 29 billion, and about 10 billion at the social cost of carbon that was in effect last year. Now, those are big numbers, and it shows how valuable the blue carbon stock is. But there's a big but here, and that is this is the estimate of inundation in the NOAA sea level rise viewer. And as the previous presentations have noted, what happens to blue carbon with sea level rise is very much up in the air. On the plus side, or I should say, I guess on the negative side, the amount of wetlands stored carbon and the amount of sequestration is reduced because carbon and marshes are destroyed and damaged, turned into open water. On the other hand, there's migration into upland areas, which creates new marsh, and that somewhat offsets the loss of marsh. However, the question that is still out there, and I don't think there's any consensus on this, is how much will the new marsh sequester, and how much has it stored because it is new. The virtue of the storage in wetlands is because they are very long lived. So how much will new wetlands be worth? Answer: something, enough to offset the losses of the older wetlands. I don't think anybody knows the answer to that question. And so unfortunately, economists can't come in and settle that debate because so much of the question depends on a delicate rebalancing in the wetlands ecology of the region. The implication of this is that the economic value of blue carbon is probably at its highest right now for the next 10 to 20 years. If the latest projections from NOAA on sea level rise in the eastern US are correct, that the expectation is that sea level rise will proceed faster up to the year 2050, and that there's greater confidence that that will happen, are correct, then there is a very small window of a couple of decades when the value of blue carbon will be at its maximum. So the time to take advantage of that is now. I would say also the lesson is don't quote those high impact numbers, because you do not really want to live in a world in which the value of blue carbon offsetting greenhouse gas emissions and climate change has gotten that high. So if you quote the higher numbers of, say, $29 billion, you are rooting for a world that you really don't want to live in. And so my recommendation is to quote the numbers based on the social cost of carbon that the Biden administration has released, which is what we did in the middle case. That's probably your best bet. And I can only say that both the economics and the science, the wetland science, say do this now, because the value of all of this is going to decrease over time. So thanks all, and I'll get out of here now. And be happy to take any questions along with my colleagues.
Great. Thank you so much, Charlie. And if I could prompt Metthea and Dan to turn on their cameras. And for anyone in the audience who would like to ask a question verbally, you can use the raise hand function that's under the reactions button at the bottom of your Zoom screen. And until I see a hand rise, there are a few questions that have been put into the chat. I'll ask the first one. That's for Daniel. Do you know if comparable work is being done on potential carbon sequestration for restored marshes?
I don't know of any specific projects, but I'm sure people are looking into it. And it's a really cool topic and probably a very active area of research, since I feel like coastal carbon or coastal wetland restoration has probably really blown up in the past couple of decades, and enhancing this sequestration takes, a long time. So hopefully there's long-term studies going on to track how well these restored ecosystems capture carbon compared to the natural ones.
So I can say that we have these 3 pilot beneficial use of dredge material projects to increase elevations in marshes. And we have been collecting, we are looking at the carbon content of the soils in natural areas, and then as the restored sites begin to revegetate, we are keeping track of the carbon in there. So it's too short of a time now to be able to make much of a comment, but we are tracking it.
Great. I don't think I see any hands risen, and I apologize if I have missed anyone, but I am going to ask a question in the chat that was put for all speakers to weigh in on. With the observed sequestration rates, have you considered the viability of private carbon credit programs to future wetland SAV restoration? In other words, are the current sequestration rates something that can qualify for carbon offset credits?
So I can, go ahead, Charlie.
I'll take a stab at that. The answer is, in theory, yes. In practice, we're still working on it. The problem with carbon offset credits is verifiability of the carbon sequestration rate. That is, you gotta be able to show that you really have taken X amount of carbon out of the atmosphere. And that has proved to be not impossible, but still difficult to attain at the standards that credit rating agencies require. So it's still a work in progress. I think that there will be much more activity in that area, but establishing the appropriate verifiable sequestration rates is we're still working for ways to do that.
I think the Veracarbon has a certified standard, and they've sold carbon credits for blue carbon projects. But I'm sure you know more about how that's actually going than I do.
Yeah, that's one of the first one that's come up, and I will say that with all of carbon credits, there are a number of different standards, but there are also a number of different requirements. People have different levels of certainty they want before buying a credit. And so there are some examples of blue carbon credits being sold, but it's still very much a work in progress.
So I know for New Jersey, it's been considered. The Nature Conservancy had a project to look at the viability of restoring marshes for carbon credits that could be sold. And I think the general consensus from a very preliminary study was that we didn't have large enough portions of marsh that fit the criteria to sequester carbon to make the project worthwhile. So not that the project wouldn't be worthwhile, but the project would not pay for itself, basically, if you were just selling carbon credits, and that was because of the size of the marshes that we have. So I think, so I know the Nature Conservancy has been considering that in New Jersey and in other states. And then as part of the natural and working land strategy in New Jersey that we're developing now, I think that will be one of the recommendations, is to look into that potential for the state.
Great. So I'm going to ask one more question. There's a few questions in the chat that have been asked, and I'm going to prompt the speakers if they so choose to answer. But I heard all three of you mention that there were research needs, and I would like for both of you maybe to spend a minute each on what the research needs are to progress blue carbon research and economic valuations forward. So I will start with Dan. We'll go in chronological order.
I mean, one big thing is increasing our point observations of carbon storage. I know that the NRCS has started prioritizing blue carbon, so hopefully there will be a lot more data points that they collect soon. And they collect a lot of vibrocore samples that go really deep into the marsh platform, so that'll help unravel a lot of the questions about deeper carbon storage. Like in my project, we collected samples at deeper levels, and the models that we used had a horrible time mapping deep storage. We could only map the surface, so there's a lot of uncertainty as we look further down. And hopefully there can be some studies of the three-dimensional structure of the marsh. I know one research group, I think around Massachusetts, was doing some things where they'd use a long wire probe until they hit sand, and then they kind of looked at the terrain and at the historical sea levels and sort of modeled how much sediment they could estimate would be stored in every area. So that's a big next step.
Thank you. I'll pass it to Metthea.
Yeah, I think there are two main areas of research that are at the forefront of my mind on this. So one of them is salinity in the marsh migration areas, both in areas where the marsh has migrated and where it will migrate in the future. How fresh or how salty those areas are will make a big difference in how well they have a net carbon sequestration. And then the other one is then having more research into the trade-offs in those marsh migration areas. So typically, a lot of times the marsh is moving into densely forested areas and the trees die and emit the sequestered carbon. So what are the, is there a net carbon benefit from marsh migration? And if so, how long does that take?
Great questions. And last but not least, Charlie.
So from an economic point of view, measuring the social cost of carbon is probably the most important, but that is a matter that affects so many different things, and is an issue of such eye-watering complexity that it probably does not deserve to be at the top of the list. From the point of view of valuing blue carbon, I would say the number one thing that economists need is everything that Dan and Metthea just talked about. and more. We need to know a lot more from the wetland scientists, because basically the economics is not all that complicated. Once you can settle on the physical and chemical issues, we can take it from there.
Great, thank you so much. Well, I'm looking forward to the Blue Carbon 2.0 session at a future Ocean Forum. And I want to give an immense thanks to the three speakers of this session. I think we all know a little bit more about blue carbon and the opportunities, and it was very exciting work, so thank you all. We are going to be moving into the poster session, so I'm going to encourage you all to stick around and check that out. And again, thank you all so much for attending today.